Alright, so this video is just going to look at some basic statistical concepts as outlined as concepts of interest on learning. So before we begin, I'd just like to say that this video isn't associated with your course. We have no knowledge of your exam or your professors or anything like that, so just look at this for general knowledge purposes only. And if you see a mistake, let me know and we'll try and fix it as soon as possible. So that said, we can start by looking at some of the factors which affect p-values and which might alter your p-value as you perceive it in your study. So we can start with looking at sample size. So if we have a very small sample size, especially considering our population, we're very unlikely to get a significant p-value regardless of the true result, because there are simply not enough test subjects in our study and in our statistical analysis. By the same token, if we take a very large sample size, we are very likely to get a small p-value, a significant p-value, even if that's not the case in the true effect. So in other words, if we add more individuals to our sample, we're more likely to get a smaller p-value, regardless of whether there is an actual change. Therefore, it's important to note that we have to be wary of, first, using too few sample subjects, or secondly, too many sample subjects in our study. You want to find a nice balance to get the most accurate p-value. The other thing we can look at is effect size. So recall that effect size is the strength of the phenomenon you are trying to measure. In other words, the difference between the groups you are trying to analyze. A larger effect size or difference is more likely to lead to a significant p-value. This means that a smaller effect size is more likely to be missed because it can lead to a non-significant p-value. So the greater your difference, the more likely you are to perceive it on a statistical test. So now we can take a look at type 1 and type 2 errors. A type 1 error is a false positive. This means that we have rejected the null hypothesis when it is, in fact, true. We can consider two examples of type 1 errors. One is telling a patient that he is HIV positive when in fact he is not. This is a false positive. Here, the when HIV status is negative, that is the null hypothesis. Another example of a type 1 error is found in the fable of the boy who cried wolf. In this fable, the boy committed a type 1 error when he incorrectly informed villagers that there was a wolf in the village. In this example, the absence of the wolf represents the null hypothesis. So type 2 error, on the other hand, is a false negative. In other words, we have failed to reject the null hypothesis when the null is in fact false. An example of a type 2 error is a doctor or physician telling a woman with metastatic breast cancer that she does not in fact have cancer. In this case, the null hypothesis is that the woman does not have cancer. So this is a false negative because we know that the woman does have cancer, but we have told her otherwise. So we can take a minute to just think about, between the two types of error, type 1 and type 2, which one would be worse? The answer, as many of you might know, is that it depends on the situation. So suppose, to start with, we are testing a new drug to treat type 2 diabetes mellitus. If we make a type 2 error, we will mistakenly reject a potentially useful drug. This in itself is not extremely devastating because there are many other undiscovered pharmaceutical options to treat type 2 diabetes mellitus, and we can take our pick of which we'd like to investigate next. If, on the other hand, we make a type 1 error, we will spend billions of dollars in funding, studies, recruitment, and more for a drug which ultimately will be unsuccessful. In this case, a type 1 error is worse than a type 2 error because we are wasting a lot of precious time and resources and money on something which is not going to work. On the other hand, suppose we have a patient with suspected invasive stage 1 lung cancer. A type 1 error would result in us diagnosing the patient with lung cancer when in fact the patient does not have lung cancer. This would result in unnecessary treatment, which could be detrimental to finances, distribution of resources, and the patient's health, emotional well-being, and quality of life. On the other hand, if we fail to diagnose and treat the patient's lung cancer, the cancer could metastasize and the patient could die as a result of organ failure. In this case, the type 2 error, in which the patient could actually die, is seen as worse than the type 1 error. This is just a schematic hopefully all of you are familiar with, looking at the reality, whether the null hypothesis is true or false, and whether you perceive the null hypothesis to be true or false. And this is a mnemonic that I found extremely useful, at least when I was studying type 1 and type 2 error. So you can see here that the type 1 error is a false positive, and it's like telling this man who is clearly not pregnant that he is in fact pregnant. This is a blatant type 1 error because it's a false positive in an individual who is clearly who clearly does not have the condition we are interested in. By the same token, we can look over here at this clearly pregnant lady and see that the physician has told the lady that she is not pregnant. This is a false negative or type 2 error because we are rejecting the null hypothesis. We are accepting the null hypothesis of absence of pregnancy when in fact the alternative hypothesis or presence of pregnancy is here. The last thing we can look at is skewness and kurtosis. Both of these refer to the shape of distribution. Skewness is referring to how symmetrical a distribution is. So here we can see a normal curve with normal distribution. It's extremely symmetrical. Here we can see two extremely unsymmetrical distributions. So we can see here this blue line is skewed to the right or positively skewed. So it's important to note that when a distribution is skewed to the right, the large bump or the peak or the apex or whatever you want to call this is on the left hand side and the tail is on the right. So when a distribution is skewed to the right, the tail of the distribution is on the right hand side. When a distribution is skewed to the left, as this red dotted line is, the tail is on the left hand side whereas the apex is on the right hand side. So that's just important to note. Now we can look at kurtosis. Kurtosis refers to, for the lack of a better term, the pointiness of the peak of the distribution. So we can see here this green line. This is your normal curve. It's mesokurtic. It has no kurtosis, or normal kurtosis, however you want to see it. This red line, this pointy red line, is leptokurtic or has positive kurtosis. So positive kurtosis refers to more pointy than a normal curve. And this blue line is platykurtic or negative kurtosis, and that refers to flat. So you can kind of think of it as plateau, flat, platykurtic. So those are just your three forms of kurtosis when looking at distribution curves. So that's it for now. Again, if you have any questions, concerns, mistakes that you see, please let me know and I'll try to address them as soon as possible. Thank you for listening and good luck with your exams.